Hello, and a very warm welcome to the Relative Spatial Location subgroup update on day 3 of the OPC Day International. This is Supratik Banerjee from VDMA Robotics and Automation, and I'm glad to present you the OPC 10210 Relative Spatial Location specification. So let's jump into the introduction or the concept idea behind the specification. The specification provides a few types which can be used as OPC UA add-ins. These add-ins can be added to instances in an OPC UA address space to bring these objects in a spatial relationship with each other. All systems that need a relative spatial location description for the objects of interest can use these add-ins in a standardized way. As the geometrical setups of systems can be very diverse, this specification provides a mathematical definition including examples of how to use the concept in the informative annex section. This brings us to the scope of the specification, which is an OPC UA information model for the representation of relative spatial locations of objects. The concept is based on the transformation of coordinate systems with the help of frames, which are typically used in robotics or vision systems to describe and calculate the location of an object or its position. Let me quickly give you an overview of the information model of the specification, and then we will jump straight into an example to show the usage of the concept. Here you see the spatial location type containing three variables, namely position, orientation, and base. This is an abstract type to describe the position, orientation, and base frame of reference of a particular object. Notice that the variable base accepts only node IDs as its values, as it will be used as a poor man's reference to the node representing the frame of reference for this object. This specification also defines a concrete subtype of the spatial location type, that is, the Cartesian frame angle orientation type, wherein the position has been defined following the Cartesian coordinate system and the orientation has been defined as angles representing roll, pitch, and yaw. A system of objects describing their own relative spatial locations is represented as a so-called spatial objects list, which is of spatial objects list type, containing an identifier for that system of objects and the origin or the world frame for this system of objects. All spatial objects in this system will be directly or indirectly linked to this world frame. Whenever a new object is added to or removed from this system, a model change event is generated. A spatial objects list organizes one or several spatial objects which are of spatial object type. This is the type that can be instantiated and added as an add-in into existing instances of an OPC UA address space. The spatial object type has an identifier for the spatial object, a position frame which accepts any concrete subtype of the spatial location type, also shown on the previous slide. It contains a folder for attach points which organizes all spatial locations with respect to which other objects may be attached, a folder for the internal frames of the spatial object, and a folder for the alternative frame chains, which we will see in the next slides. Let's begin with an example for you to familiarize with the terms used in this concept. Let's say that we have an empty room and the purple frame is the origin or the world frame for this room. Derived from the purple frame, there is a green frame, which is the position of this table. Now let's say that this corner of the table will serve as an attach point with respect to which other objects can be placed on the table. For example, this chessboard. The green frame on top of the table represents the position frame of the chessboard. Similarly, you can imagine 64 attach points on the chessboard. This brown knight is placed on one of the attach points, but its position frame is oriented a little differently. Similarly, this white king is placed on another attach point with an offset. And this brown king is placed exactly on top of another attach point. This brown queen is out of the game and is lying freely on the table. Therefore, its position frame is represented with respect to the attach point of the table. You can also see small attach points on the heads of these figures, with the help of which these figures can be dragged or picked up by another tool. Now let us try to model this table with the tools provided to us in this specification. Note how the specification uses the constant bit in the axis level x attribute of the nodes. If the spatial location of an object itself is fixed, then the constant bit of the variable representing the frame itself is set to true. To denote that the frame of reference is fixed, the constant bit in the variable base is set to true. This is represented like so in the model below. Constant is for the frame itself and constant base is for the frame of reference. Considering this table as the system, here you see a spatial objects list representing the system with the world frame, that is the purple frame, as the origin of the system. This table has a spatial object add-in which describes its position frame and its attach points. Note that since the world frame is the origin, it has no frame of reference. Therefore, the base variable of the world frame must be null. As you can see, since the attach point is defined with respect to the position frame of the table, which in turn is defined with respect to the world frame, this relationship can be established by following the poor man's reference, that is, by hopping to the nodes mentioned in the base variable of the respective frames. These chains are shown in green. Here is the complete model of the example shown earlier. All objects in this system describe their relative spatial locations with their respective spatial objects. Each spatial object describes its position frames and attach points. Let us understand this from the perspective of the white king. The white king has an attach point called head, the position of which is with respect to the position frame of the white king. The position frame of the white king is described with respect to the position frame of the chessboard. The 64 attach points of the chessboard has not been represented here for the sake of simplicity. Now, the position frame of the chessboard is defined with respect to the attach point of the table, that is the table corner. And so on until you reach the end of the chain, that is the world frame. It is important to note that in addition to the attach points, the white king also provides an additional way of representing its spatial location, that is directly with respect to the world frame. And this is exactly what is represented in the alternate frames folder. This is another example to show the usage of this specification in a multi-server scenario. Imagine a scenario where you have an OPC-UA server for the chess room with 2 playing stations in it. You also have 2 separate OPC-UA servers for each of these playing stations with their own chess tables and their own world frames. This specification gives you the possibility to relate the different spatial objects represented in the different servers. This is where the identifier comes in. Note how the value of the identifier of the spatial objects list in this server is the same as the value of the spatial object in this server, thereby meaning that a whole system of objects that is represented by the spatial objects list in case of this server is the same of the spatial object of a single spatial object in this server. Hopefully it is not so difficult to see how this same concept can be used in an aggregated scenario with multiple levels of abstraction, just like in this example. Now I would like to give you an overview of the use cases supported by this concept. The concept supports building of frame chains describing the placement of objects in space based on common or different reference coordinates. The concept supports identification and mapping of reference coordinates usable for controller-to-controller process communication, for example, a robot with a machine vision system, or which is usable for aggregating server scenarios. The concept supports dynamic aspects to enable a client to be aware of changes in the relationship of objects, or when objects dynamically appear or disappear. This concept can be used to describe the relative spatial relationships of each object, which is based on some reference coordinates. The definition of each object in space is self-contained, describing its location related to that reference coordinates. Well, that's it from my side for today. In case you have questions, you can shoot them right now, or you can also contact me at the contact details that you see on the screen right now. Thank you, and have a very nice day.